All right. Hello, everyone. My name is Jonas. I'm a research scientist at Google DeepMind. And today I'll be talking about unlocking modular continual learning. I'll talk about its core concepts, open challenges, and some future directions that I find interesting. So we need a paradigm shift. Current models are massive and ever growing. And specifically, when we continue to fine-tune these huge models, this becomes extremely inefficient because this creates isolated models and copies of them for every single task or domain that we're fine-tuning on. Simultaneously, in context learning and prompting has limitations. It's often inefficient, given that we would have to create prompts for every single scenario. It's sensitive, and it's often lower in performance than if we would fine-tune the model. And simultaneously, we have existing sequential learning challenges such as catastrophic forgetting or catastrophic interference during multitask learning. And so we should think about moving beyond like these monolithic systems towards a model or an AI that is efficient, meaning that we have lower parameter counts per task so that we can adapt faster. We want to seamlessly integrate new knowledge into the model without forgetting, so continual learning that model. Ideally, it should also be collaborative. Collaborative is more general here. That means it doesn't necessarily have to be collaborative in the sense that we distribute it across people around the world, but can also be collaborative in the sense within a company that different teams collaboratively improve the model on the respective domains or tasks and so on that they're interested in. And the same goes for decentralized. The different teams or different institutions around the world shouldn't necessarily have to interact with each other very closely, but be able to independently work on the model and improving it continually. So the aim of my talk today is not a survey, so I'll not talk about all the amazing work many of you in the audience have been working on. It's more of a higher level concept and direction. I'm trying to synthesize the core concepts of where the field is moving into. And a caveat is that I will not be talking about distributed pre-training at all. I think my predecessor has talked about that a lot, and we see a lot of the challenges that come within distributed training. So that alone is a challenge in itself that's very difficult and is very important. But in my assumption is like there is a model, what the architecture should look like in a modular system such that collaborative continual learning can actually work well. So assuming, for example, that a big team actually trains this model is kind of a default that we've established that works very well. It's a very difficult challenge in itself. So this is kind of orthogonal to all the previous talks that we've heard there. I'm trying to understand where the challenges and opportunities are specifically for this continual learning scenarios in modularity. And hopefully this will spark some new ideas for you to go out and merge some of the ideas that exist maybe in somewhat orthogonally related research directions. Okay, so first of all, I'm going to talk about these computational modules, where the idea is to encapsulate knowledge into specific modules. What are they? How do we build them? And where are the limitations of these modules? We're then going to look at how do we combine knowledge. So there's independent research going on. One is dynamic input conditional. The method that people use in this dynamic scenario is often routers. So basically on the token level, a selection is made dynamically. And the alternative direction is static, which is parameter merging, combining modules directly, and this is often done very statically, meaning that it's done before inference time. Then we'll talk about continual learning within modularity. How do we learn over time? How modularity can actually help in continual learning, and look at some of the challenges that we're facing within this continual learning in modularity. And finally, look at some of the open frontiers within that space. Okay, let's first of all look at the computational modules. So essentially, in my opinion, anything that forms a distinct, often parameter efficient, computational unit for a specialized purpose can be a module. So anything that is very specific to one thing is a module. For instance, parameter composition. So that means it's like a subnetwork within the existing model. It can even be the entire model itself, but when you're kind of adapting the existing model or sub-parts of that model, like lottery tickets or LoRa's, those are obviously modules. Input composition is also a module. So prompt tuning, prefix tuning, in-context learning, or just documents that you retrieve through RAG are also modules. And the more intuitive thing that people probably predominantly refer to or think about modules is functions. These are, for example, adapter layers or MOE experts, but also LoRa's. The difference between LoRa's and the parameter composition version is that here the argument is that you actually project it back to the original parameters, whereas how it's used in practice is more just having a bunch of LoRa's and then they're no longer really parameter composition, they're kind of independent functions that you activate in parallel. So it's kind of, LoRa's fit kind of to both spectrums there. All right. Now let's look at the most popular modules that exist. So even though there's these broad families, the dominating architecture currently is either an adapter or a LoRa. And here the general notion is that you have a pre-trained model and then you add experts to the model after the fact, meaning that you actually freeze the pre-trained weights and add components that you only fine-tune on the respective task. And on the other side, you have mixture of experts where you actually focus on scaling up the capacity of the model and learn feed-forward, the respective feed-forward networks as the respective experts together with a router. The difference is, one on the left side is adaptation, where you train modules for adapting an existing model. And on the right side, modules are integrated for scaling, so increasing the capacity while maintaining the activated parameters. And the important thing here is that a large portion of the parameters are actually shared, meaning that for every single task or domain that you're fine-tuning on, a large portion of the model is shared. On the left, with adapters, the amount of parameters that are shared is considerably higher than on the right. So adapters argue for being parameter efficient, often only accounting for 1% of the parameters in total, whereas MOEs are the modules or experts account for significantly higher portions of the parameter count. So this was, I think the audience knows about these concepts quite well. But the problem is that modularity is often an afterthought. So we design adapters for adaptation to a single task. and we adapt an existing model that was not designed for modularity at all. So actually, if we have a monolithic model that is dense, then the mixture that we pre-train on, in this specific example, it can be multilingual. We actually experience interference across the different distributions that we train on during pre-training, meaning that the largest class, the largest distribution, grabs the majority of capacity, and often the tail end of distributions actually results in a significant drop in performance. And simultaneously, we actually create a Frankenstein model when we suddenly then add these adapter modules that are not necessarily designed to be added at that specific position. And we see this specifically in scenarios where we actually design the model to be modular from the get-go. Here, an example for multilingual pre-training, where we add modules during pre-training, and we find that this actually improves the per language performance, and it allows us to add more and more languages down the line, even though the model has not seen that language or language family. But if you add adapters to that monolithic model that has been pre-trained on all languages, these modules cannot mitigate the interference that has happened during pre-training already. So the design of a modular architecture from the get-go does actually disentangle these distributions and simultaneously allows us to add modules in those slots further down the line. So this is an evidence that designing a modular architecture from the get-go has some very positive benefits. So many of the open research questions are what defines and this is specifically questions that arise for modular design for pre-training, right? So not necessarily ones that address like adapters, but how do we design a modular architecture that we add during pre-training? So what is a modular, optimal modular architecture? Does it have to have bottleneck? Is it a bottleneck adapter? Is it a full layer? And this specifically for different goals: task specification, language, general capability, and so on. Simultaneously, should these modules be homogeneous or heterogeneous? Should the capacity of the architecture be different? This is basically a big scaling problem. Current research focuses on homogeneous architectures because it's just much easier to implement and deploy. But that's maybe not the ideal scenario if you want to do continual learning across many domains, modalities, and so on. How many parameters should be shared? How many should be modular? MOEs have high capacity for modules. Adapters have very low capacity for modules. Yeah, if the respective design choices, how they impact compositional generalization, and also if we actually design the model to be integrating adapters or modules for adaptation in the first place, how does that affect adaptation further down the line? If these slots already exist, does that improve performance? My hypothesis is yes, rather than adding these modules after the fact. And by designing these modules, this model in a modular fashion, does this actually encourage the emergence and disentanglement of these distributions such that we can reuse the skills, for example, for multiple languages or tasks and so on. Okay, so the next part is about knowledge combination. Yeah, basically we have these modules and how do we then combine them? And there's again two different directions. The first one is dynamic input combination. So at runtime, we have multiple modules available. How do we select those respective modules dynamically? And here, flexibility is prioritized, meaning that we just provide the model with all the modules, and at inference time, it can select the respective modules. In parallel to that, we have this static global parameter combination. Here, inference is more at the central priority, meaning that we would like to combine many of the parameters for a specific target use case. And obviously, these are not strict. There's movement between them. You could come up with methods that are predominantly for static merging that become more dynamic. But the methods here are predominantly used in this kind of fashion. Okay, let's first of all look at that part. And you know, the classic approach is sparse MOE style, meaning that both modules and routers are trained jointly. And we select a top K set of tokens for their respective input sentence. This scales very well. Load balancing allows us to increase the total number of parameters while maintaining the flops. But it has a lot of issues with respect to specialization. This load balancing loss does not actually result in specialized experts, and often the experts become redundant. So there are a lot of emergent ideas in this direction. So upcycling these modules in Nexus, I wasn't here, but I think maybe that talk was given earlier today by Ahmed. Then there's also directions of reducing the effect of this load balancing loss. So having auxiliary loss-free balancing. And there's also other directions of actually merging some of these experts after the fact and making them more modular. Here the general direction is let the model figure it out, how to learn these respective modules. Simultaneously, you could also go in the direction of training adapters or modules independently of each other, having a set of LoRa's trained on the respective domains, and then trying to merge them or route between them after the fact. Here, a bunch of recent works like Fat Goose or Arrow try to learn router weights after the fact or on a few examples, so that the model can then use those for a specific example to select which LoRa or which module is most useful for the respective downstream task. In order to mitigate or circumvent that, we can also do some attention-based aggregation, meaning that we pass through all experts and then learn an attention mechanism based on the output of each of the experts. Removes the necessity to have router weights, but requires us to pass through all experts, which is extremely expensive. There's a very good survey paper by Yadav et al. That kind of talks about all these different methods. These are just two of many, many methods. So do check out that paper if you're interested in this direction. All right, and I also want to point out that the adapter hub was kind of one of the first multitask models that allowed us to actually upload independently trained adapters and merge them after the fact. So everybody around the world could download a Hugging Face model, add an adapter to it, upload it to the adapter hub, and then define new parameter merging, adapter merging, routing techniques to come up with a better merging method. So kind of old now. PEFT is great for that as well. Okay, let's look at the second direction, which is static global parameter combination. And here, the idea is to combine the modules or the entire model in an offline kind of fashion and unify the model. Basically, the inference time of a merged model is equivalent to the original model, which is not the case for a router-based method. So simple averaging works quite well Then there's task arithmetics, where you can add and subtract task vectors. And then there's other methods that try to mitigate this interference. So if the issue with these methods is that given that you're fine-tuning the respective modules on, to some degree, orthogonal tasks, and average all the weights, then there's obviously interference within the weight space. And so many methods that are also presented at ICLR this year try to mitigate this fact, basically identifying which parts of the model are interfering with each other. So ties merging is one of the most popular methods, but there's also methods that I think were presented this ICLR that actually try to design the task vectors that they actually interfere with each other less. And all these methods rely on the assumption that there's linear mode connectivity between the weights, meaning that all the models that were trained on the downstream task are within a loss basin that is connected. Okay, so let's look at these two concepts and open questions. So is there a way, is there a trade-off between this dynamic routing, and is it always superior to static routing, or vice versa, depending on the scenario that we're actually interested in? So for continual learning, what is better? Collaboration, efficiency, out of distribution generalization. In what scenarios is one version better than the other? How do we actually achieve robust specialization selection of these mixture of experts or post hoc routers? How can we efficiently scale up the number of diverse modules? So all the papers that we've looked at here use, I don't think, more than 100 experts. And these are very parameter efficient. If we scale this up to all the distributions that we have, or all the individual tasks that different teams or industries are interested in, then this does not scale anymore. It's very difficult to then actually route across these diverse modules. And this also assumes that the modules are actually homogeneous. There's no method that I know that actually acts upon on heterogeneous architectures, that learns a router on 5 tasks that had a LoRa adapter, another 3 that had bottleneck adapters, and another few that did prefix tuning. So how do we effectively handle a scenario where we get thrown in multiple different heterogeneous systems? And simultaneously, existing issue which was addressed here at ICLR is interference. So if in static merging, if we train these modules on many different tasks, there's bound to be interference. Most of these methods, I believe, work well if you have a handful of tasks that you train on. But assuming that you have thousands, I think none of these methods really work well in a specifically continual learning scenario. This specifically goes for kind of orthogonal knowledge that are integrated in the models where interference happens even more. And finally, how can we find synergies between these two methods? Can we develop methods that effectively blend the dynamic selection and the static merging? So basically, which models should we decide to route, and which should we decide to merge? Depending on what you're interested in or what the respective modules or parameters have learned, I think one method should work better than the other for the respective parameters. Okay, let's look at this. These methods were kind of independent of continual learning. These were task adaptation, routing challenges. In the context of continual learning, the goal is to, given a stream of tasks, how do we learn the stream of tasks without catastrophic forgetting the previous knowledge and effectively adapting to new information. So modularity here can help for knowledge isolation, meaning that we integrate the new knowledge into these specific modules. And we can efficiently update the model because we're just adding modules rather than copying the model further down the line. So we want to select in dynamic routing the relevant old and new modules for a given input. And in parameter merging, we want to integrate the new experts into the existing model. So here, if we contrast this to existing continual learning, these models often struggle with plasticity, meaning plasticity is basically gaining new knowledge under computation constraints. Methods like rehearsal, meaning that if we continuously train on more and more tasks, we provide the model with the old data continuously. That's effective, but often violates some of the CL scenarios. PEFT methods or modules, like function modules, they offer good stability. They forget less or forget nothing if you think about it. But it's difficult to combine them at scale. However, they do outperform multitask learning quite strongly. If you look at merging methods, they're still a very great baseline. They balance this knowledge accumulation, and they scale well because the total parameter budget remains the same, but they just don't reach the multitask learning performance. So there should probably be a trade-off between the two methods. So challenges and open questions for this modular CL. How do we design modular systems that continually learn over long horizons, that maintain this knowledge acquisition, and adding new knowledge and stability for old? And how do we quickly and effectively adapt to new domains? What is the optimal trade-off of added to modified parameters? And which combination is the best here for this adding more and more modules? So I want to now more broadly look at this. So is there a way for us to actually integrate all of this into the system of continual learning from the get-go? Can we design a model for continual learning so that it encourages the model to disentangle complementary capabilities, for example, reasoning capabilities, into the shared parts, and store the idiosyncratic information into maybe even heterogeneous modules? And how can we encourage adaptability for dynamic combination, so routing of probably modules, and static combination of probably shared parameters? But in order for us to design this, we definitely need to go beyond accuracy. So standard continual learning metrics like accuracy, forgetting, and so on need to be extended to how efficient it is to add new modules, how well does it compose and generalize to different distributions, and how robust is it for merging and routing over time. All right, so concluding, I have to be fast here. Yeah, modularity is a powerful paradigm, and designing modularity from the start is probably a great direction. And these are some of the research frontiers that I've discussed. We're hiring a student researcher. I'll go back to that slide in a second. This is based on modular deep learning, our website. We have a great survey paper A lot of my slides are based on the work of these researchers and many, many more. Here's the QR code again.
Yeah, thank you so much for the talk. Really, really interesting. I'm wondering, you mentioned interference, and I'm wondering, in your opinion, should we work on developing models that interfere less? Say, specifically for continual learning, you can develop systems that have a disjoint expert for every task, and then hence you don't have interference at all. But then in that case, you don't actually gain anything from, say, transfer learning because you can't actually build on what you learned before. So, in your opinion, what is the optimal model?
I had a comment on my slide, add transfer, and I forgot what I wanted to say, and that's specifically what I wanted to say there. Thanks. So yeah, I think it's very important for the model to have the necessity of sharing relevant information, but having the capacity to learn idiosyncratic information. So that's my specific method was always to understand what is the minimal amount of parameters that has to be modular, so that the model learns this idiosyncratic information there, so that the most knowledge is stored within the shared parameters, such that reasoning and so on are basically there. So this transfer across distributions and shared knowledge is, and shared reasoning or whatever you want to call it, should definitely be part of that. I think that's a core principle, yes.
Thank you for your talk. I'll ask you a non-modular question. So what if maybe you followed also the mixture of LoRa's trend that happened last year on both text and image? So, sadly, I didn't dive deep into the ones, like I noted a lot of new ones that I hadn't found today. So the first question is, can you comment on any similarities or dissimilarities between these mixture of LoRa techniques and what you presented today? And then the other question, which is I think works both on modular and non-modular, is what if there was an infinite mixture of adapters?
Yeah, so I think most of these mixture of LoRa methods are very relevant to this. They're different ways of merging, routing between LoRa's, trying to mitigate interference, trying to share knowledge. I think the main focus is often compositionality and not so much on continual learning. So I think these methods can all be applied to that direction. An infinite mixture of experts. So honestly, like, I think if we have infinite compute, infinite data, infinite everything, we don't need anything modular. I think that that's not the case, and efficiency is important. We want to do everything faster, and integrating kind of an inductive, architectural inductive bias into the model will help it learn. And I think that's the key part. We don't have infinite resources, and therefore designing this in this fashion will help the model learn faster.